not come up? Okay. It will in a sec. So built into this PowerPoint presentation, there are some questions that are going to help us kind of follow along and figure out what's going on. The questions are set up so that everybody in here is going to be able to respond to them. You're going to be using these devices here. These are called clickers. These just communicate directly with the computer. I can tabulate responses, and what will happen is we'll have a question that shows up on the screen. The answer choices A, B, C, and D will show up on the screen of your own clicker, and then you can pick whichever one it is that you believe is correct. Put that in, and then I'll be able to show you as a class how everybody did. And you can sort of see how your answer fits in with everybody else's without having to raise your hand and commit to something for everybody to judge you on your ability to answer questions. So to get this started, everybody needs to grab one of these things, which I'll have you do in a second. And I have to get the whole thing started. Once I get the system operational, you'll be able to log into the clicker by holding down the menu button for a couple of seconds, which is in the top corner here. It'll flash some stuff up on the screen, ending with enter user ID. Your user ID is your student ID number. If you have that handy, you can put it in. If you don't, I have them, and I can give it to you. So I'm going to go click on all this stuff to get it set up again. While I'm doing that, everybody come up here and get one of these out of this suitcase. Do not grab the ones that are upside down in the back row, because those are dead batteries. Okay, so on the clicker, the menu button in the top corner here, hold that button down for a second or two, and you'll see some stuff come up on the screen, ending with enter user ID. And like I said, your user ID number is your student ID number. If you don't know it, I have it here, and I can give it to you in a sec. But if you do know it, go ahead and type that in. It starts with a 0 or maybe 2 zeros. You can leave those off if you want, because the computer actually ignores them. And then the send button, which is the one with the 2 arrows below the menu key, press that, and that'll put your number into the system. Anybody that needs their student ID. So you are 232. Anybody else? Wow, great. So once you log in, once you send your your student ID number in, I can't remember if anything flashes up on the screen, but it'll end by saying Quizdom, which is the name of the system with the W instead of the U. When we get to a slide in the PowerPoint presentation that has a question, yes, thank you, question. The clicker screen will then switch to having A, B, C, D as the answer choices. Obviously, the 1, 2, 3, and 4 buttons are also A, B, C, and D. So push that button. It'll highlight your answer choice on the clicker. If it highlights something that you didn't mean to click, then you can just click on something else, change your answer there. The send button will then submit your answer to the computer. And you will only see the letter for whatever you submitted when you've done it. So when you see only one letter on the clicker, you know you've done your job. Okay. Now, you can't quite see it on the screen here. The send button is the one with the 2 arrows underneath the menu button. You can't quite see it on the screen here because the screen's pulled down kind of all the way, but this little thing right here is actually a gray bar that has the stats for this. And from it, I can pull up a little bar graph showing how everybody voted, if you will, on each question. It won't give any personal information. It'll just say how many people chose A or B or C or D. And that'll just give us a little perspective on where people are with this material. Now, the reason we're doing this is because here, this week, we're doing Chapter 2, and next week, we're doing Chapter 3, is really the part of the foundational aspect of this course. I really should be able to assume coming into this class that you have a background in basic chemistry and biology. The prerequisites for this course list high school chemistry and biology or some introductory courses here, which is Biology 102 and Chemistry 101, I guess. Actually, I should say Biology 102 is going to change numbers to Biology or Bio 101 next semester, but that's not important. The way that's worded, it actually means that you don't have to have completed any classes to come in and take A&P1, which is sort of unfortunate. The school kind of, or not the school, but the way that this course is used in some respects at the school is as a weeding course. So people are in A&P1 because they're planning on taking A&P2 because they need that as prerequisites, A&P1 and 2, as prerequisites for some sort of health program that they're going on to. The health programs are quite competitive. The numbers that I'm familiar with, which is getting to be quite old, probably about 5 or 6 years old now. 1 year, 1,200 people applied to the nursing program here at State. Of those, 80 people were accepted. The limiting factor on how many people can be accepted into these programs is how many faculty they have. They don't have enough faculty to teach more than 80 students. It would seem obvious to say, well, why don't we just hire new faculty? The problem is that you get paid more to be a nurse than to teach nurses. So it can be kind of challenging to hire good faculty. They have to be willing to take a little bit of a pay cut. So there's not as much space in the program, and nursing is just one example, as there are people trying to get in. Now, of those 1,200 people, half of them actually didn't really even get to the point of applying because there's this admissions test, I guess you could call it, kind of like an SAT, but for nursing. And it's changed over the years. So what it is now is a different name from what it was the year that I'm talking about.
Is it a TEAS test now?
I don't know what it is now. But it changes over the years. So whatever the test was back then, only about half of the people in that 1,200 that I said even got a score to be considered for the nursing program. So really it was 80 out of 800 viable candidates, which is still a 10% acceptance rate, which is about what it is getting into like a medical school or something like that. But that 1,200 is assuming people had taken the prerequisites to get into the course. And so if we really go back and look at how many people applied, how many people started A&P, originally, probably there were like a couple thousand people that were planning on applying to the nursing program. And unfortunately, we kind of use, and not intentionally from our department's perspective, use this course as a weed out course. If you can't make it through A&P1, then you're not going to go on through the rest of it and you realize you're not going to be applying for whatever program. Personally, I think it's a horrible way to do it. And I don't really support it. And in fact, the course is made to be sure that you get through A&P1. Okay. I kind of talked about this back on the first day, way back when. If you do the material, all of the work that's expected of you to the best you can, which is the part 1, 2, and 3 assignments and the lab quizzes and those sorts of things that you have multiple attempts on, do those over and over again until you get the best score possible, you're pretty much guaranteed a C- going through this course. Okay. Now, that does require a good bit of work, so it does weed out people that aren't willing to do the work. But if you're willing to do the work, as far as I'm concerned, you're going to pass A&P1 enough to be able to go on to NP2, and then my NP2 classes are set up the same way. So you can at least pass through those. Now, whatever program you're planning on going into, a C- probably isn't going to cut it. So you do have to do a little bit more work. For some people that are going to say like AIC, they just have to have a C+. Okay, that's sort of the cutoff. Anything below a C+ is kind of ignored, treated as if it was an F. But if you have a C+ or better, then you're potentially a competitive applicant. Here, generally speaking, it's said that you need A's, but I can tell you from personal experience that I've had students that are C students have gotten into the nursing program here, or people that have been competitive for the nursing program end up getting into some other program. Okay, so aside from the dental hygiene program, what it says on paper is not the final word. There's more to it. Yeah.
Yeah, I'm planning on applying to grad school at UMass. And does the same thing apply? Or,
there's so many variables there. Like when I applied to graduate school, I was a psychology major with a bio minor. I had a 2.9 grade point average across the board because I was originally a computer science major and I really bombed out on the math stuff. But within my major, I had a 3.7 or something like that. So as far as graduate school is concerned, there's a whole lot of room. You can spin stuff as far as things are concerned. And with graduate school, oftentimes, letters of recommendation carry the most weight of anything. So, but if you're interested, we can talk about that individually, because I do have some experience in that myself. But anyways, the point being, back to what we're really talking about here is I should be able to expect that you have some basic chemistry and biology information coming into this class. But it doesn't always work out that way. And a textbook like we're using, or like any other of the courses here we use, they always have these introductory chapters like our chapter 2 and 3, which are on these topics. It's not really feasible to go into a lot of depth about this material. So what I'd like to do this class meeting and our next class meeting on Friday is to sort of touch on these subjects and kind of highlight what I think is most important. In the book, in the material that you have, and the assignments you're going to have, they'll get into asking more in-depth questions. And again, the way that I designed the course, if this is a topic that you're going to struggle with, you'll have the opportunity to put the work in to get the grades out of this section of the class and move on just fine. But I do want to spend a little bit of time doing that. A lot more preamble than I meant for this. But this is called a, quote, case study, which means that it's just kind of a story. It's a little silly, but in the end, I think it's going to be pretty useful for what we want to do. It says bonding with a tutor. What it is, it's a story about a student who goes to a tutor to get help with some basic chemistry stuff about how atoms bond. So we're going to walk through this case study. A lot of it is a little bit, underwhelming. There's a lot of pages of text like this, which if I were making a PowerPoint presentation, I would never put this much text on the slide. But that's the way we have it here. So I'm going to let you read through this. I'm going to put this model back in the back where we need it. I'm going to cut off some of the lights so we can see the screen better, and we'll go on with this. So go ahead and read that. So the story here is just this guy, which one is it? Nick, who needs to get a little better grasp on chemical bonds. So he's going to this tutor, Josh, to get some help with this. And so we're just going to walk through this story, essentially. And there will be certain places where it explains things, and there will be some pictures to go with it, and some questions, again, about what's going on. Now, having this as sort of our case study, I do want to mention we have tutors available on campus if you feel you need additional help in this class. If it's the basic chemistry and biology stuff that you have, you need to get some help with, there are a number of tutors that are capable of doing that. We have a couple of A&P specific tutors, maybe even 3. But for this initial stuff, if you're struggling with the chemistry and biology aspect of it, there are intro biology and intro chemistry tutors that you can go to. This is all down in building 27, which is the building with the library. And I don't know exactly where it is now, but there's an information desk right there in the front of the building, and they can direct you where you need to go. Question?
If you have like questions that aren't related to a class, I'm trying to also learn some basic electronics. Would there be tutors in those fields, or just in like the sciences?
I'm not sure exactly what all of the tutors are. If you go to that information desk, they'll have a list of the tutors, or they can direct you to the person. I looked over the list that was emailed out a couple of weeks ago, and I saw that there's like 2 or 3 people that do A&P specifically, but then there are other people that do intro bio and intro chem that can answer some questions. Okay, so Nick claims to know about one of the bonds, but he needs to understand things a little bit better for the other ones. Now, there was a time, actually, before I started teaching here, where the chemistry department over in Building 17 actively told us in the biology department not to teach anything about chemistry. That's actually kind of impossible. You can't really approach biology, even at the intro level, without understanding some of the basic chemistry behind it. But what they found is people would take our Biology 102 intro course, and then they'd go over and take Chemistry 101, and what they learned in our class would be confusing with what they teach over there. And instead of telling us not to teach chemistry, which, like I said, is really impossible to tell us to do, rather, I think it's better if we, in the biology department, explain how we're teaching chemistry. So I want to talk about that a little bit. And this electron shells thing has to do with the root of the problem. Now, in this just verbal explanation of what electron shells are, it kind of starts to paint a picture. But the issue here, and really the issue that's the root of the problem between biology and chemistry classes, is what it really means when we say this kind of stuff. To understand this level of information, we need to deal with what we would call a model. Now, you're probably familiar with what models are. So, for instance, this is a model of part of the respiratory tract, or this is a model of the torso, et cetera, et cetera. Models aren't necessarily physical representations like this. In fact, the human brain works by modeling things pretty much all the time. I can tell you to imagine that class is over and you're going to go home. When I say that, in your brain, you're going to automatically start to imagine where your car is or whatever type of transportation you're going to use, how you get to that, where you're going to walk, whether it's down the hill and across the street or go to a bus stop or something like that. And you'll imagine the path that you're going to drive or the bus is going to follow to get you to your house. And you go to your house. All I said was, after class, you're going to go home. In your head, you have a model of where that transportation is, where you parked your car or whatever, and a model of the city or surrounding cities, wherever you might have to live, to get to that location. And that map is a model. In fact, a physical map is a model. Okay? Whatever it is, it's a way for us to understand something that's out of our scope of understanding. We can't step back and look at the entire greater Springfield area and see, okay, there's Stick and there's my house, or something like that. We have to internalize it into our heads. Now, with that, we're kind of imagining how we're modeling something larger than we can encompass in our own experience. When we're talking about atoms, it's the other direction. Atoms are too small for us to experience directly, for us to say what they're like. We have to use tools to do that, and even then the tools are at best suggestive. You can't look at an atom and say, oh yeah, that's what an atom looks like. So for us to have a visual representation of it, we have to develop a model. And this is a model. Okay? It's two-dimensional. It's a drawing on a screen, of course, as opposed to these three-dimensional models that we have for anatomy. But still, it's a representation of something that we can't necessarily see directly. And I should say something, since we're talking about anatomy models, this torso model isn't representing something that's too big or too small for us to see. Rather, it's representing something that we can't look at directly. We can't take somebody's body and open it up. I mean, we could, that'd be a cadaver dissection. But it does require somebody to die to get there. And we don't want to do that. So this is a model representing what's inside the body in a way that we can't directly experience. So we can look at these things. It's the same thing we have going on here. Now, this is basically the root of the problem that the chemistry department has with us. This is a very old-fashioned model of what an atom looks like. When we talk about electron shells, in this model we're talking about an orbital. And this is the orbital model of electrons, or the planetary model. That in the center, there's a nucleus, represented in this picture by the Na, representing the sodium nucleus. And orbiting around that are these rings, concentric rings of electrons. If you go over to Building 17, take chemistry over there, when they talk about electron shells, they don't talk about orbital shells like this. They talk about a different geometry, which is a little better representation of what's really going on in an atom. We can't know exactly what's going on inside an atom, so the models are just better and better approximations. Okay. This approximation is the best one we need. Okay. It's going to tell us everything we need to know in a biology class about atoms. It is inadequate. It doesn't tell us everything about atomic structure, but it does give us enough information for us to understand what's going on. Okay. And that's the root of what most of this case is going to show. So I don't know what speed any of you read at, but what I'm doing here, just to give everybody enough time to read, but not spend so much time that we never get through this, is I'm actually just reading the things myself. I'm not the fastest reader. So if I've gotten through the slide, I can assume you have, but then also obviously I'm talking a bit between slides. So if you're reading slower than I am, then you're going to have a chance to see everything. And what they're saying here again is they're talking about these shells, and the innermost shell can hold 2 electrons. It can't hold more than that. So if we need to put more than 2 electrons in an atom, then we got to move out to another shell, and we'll just start filling that shell up. And in the case of sodium, we need to go out to a third shell. Okay. Now, when we're talking about how many electrons there are in an atom, generally it's based on how many protons there are. And the number of protons in a given atom is always going to correspond to its atomic number, where it is in the periodic table of elements. So sodium, for instance, is element number 11, which means it has 11 protons. And atoms generally are going to be electrically balanced. They're going to have no net charge. So for the 11 positive protons in the sodium atom, we need to have 11 negative electrons. And so the picture we were looking at a second ago, where we see the shells filled based on that. First one can hold 2, but obviously we need another 9. So the next shell out can be filled up with 8. And we still have 1 electron more to go. So then the next shell out, we put that last electron. So that last shell, the one for sodium that contains only 1 electron, would be what we call the valence shell, because it's the outermost shell. For atoms to enter stably into bound states, to be parts of molecules, they want their valence shell to be full. Now, in the case of sodium, which we'll see soon enough, that third shell will actually kind of disappear because it'll lose that electron. And then its outermost shell will be the second shell, which has 8 electrons in it, and it'll be full. And then it'll be, as it's described here, as unreactive or inert. So in the case of sodium, what I just described would be the valence shell contains 1 electron, and it'll lose that electron to another atom so that it will have a complete outer shell, which happens to be the next innermost shell, okay, which is what's on the outside after that 1 electron is lost. So who can give me an example of what a noble gas is? Names of noble gases.
Hydrogen.
Sorry?
Hydrogen.
No.
Noble gas.
No.
Helium.
So the first row in the periodic table has only 2 elements: hydrogen, the first row, and helium in the last row. Helium is a noble gas. What are other noble gases?
Argon.
Argon, what else?
Neon.
Neon. I had to ask because there's another one that sounds very much like that. Xenon. Right? So there are others. There's krypton. I think radon's up there, something like that. But they're all in the final column in the periodic table. As we're going across the periodic table, each column represents essentially a particular number of electrons. The first one represents, for the valence shell, 1 electron. Okay. Hydrogen only has 1 proton, therefore it only has 1 electron, which would be in its valence shell, the outermost shell. And then we'll skip over lithium because it's not that important, but we were looking at sodium a second ago. Sodium has only 1 electron in its outermost shell. Same idea. The second row is going to be 2 electrons in its outermost shell. The third row will be 3 electrons on the way across until you get to the last row, the last column where there will be a full valence shell. Now, for that first row, which is hydrogen and helium, that first shell can only hold 2 electrons. So there's only 2 elements between in that row. And there's a big gap between them. The second one, there are 8 elements. And the third one, there are 8 elements. The fourth one, I think fourth is still 8. But somewhere in there, there are more and more added in as atomic structure gets more and more complicated. Fortunately for us, we don't have to worry about that complicated atomic structure. The atoms or the elements that we're most interested in are all going to be fairly close to the top of the table. Hydrogen, which we just met, which is number 1, it's in the top corner. And then in the next row, there's carbon, nitrogen, and oxygen, which are all kind of in a row there. They're very important ones. And then a few other ones in that neighborhood are also going to be important. So now if you look at your clicker, you'll see that there's now answer choices available to you on the screen. So based on this question, put in what you think is the appropriate answer. Now I want to wait till everybody to put an answer in, and then you can't see it on the thing up there in the top, but it tells me percentage-wise how many people have responded. So I'm going to wait until there's 100% responses. Okay, there's only 76% responding so far. So if you haven't put in an answer, please do. And if you think you've put in an answer but you haven't, you'll know because you'll still have 4 letter choices in the screen. When you've put your answer in, only 1 letter choice will remain. Great, now we're up to 100. So what I can do with this bar that you can't see here, I can actually have it pull up a histogram showing the responses. Okay, so we see a couple of responses to A, 7 responses to B, response for C, and a few responses for D. So back to the answer choices here. Which one of those is correct? B, right. Remember I said a second ago that the first shell can hold up to 2 electrons, and then the next one can hold up to 8. So basically here we have 2 shells in all of these choices, and we're looking for the one that has 8. Or we could also say the one that has the most. Okay. Now, in choice A here, it looks like there's a nice even distribution of electrons, and it would suggest that it's full. But in fact, there's only 6. It needs to be 8. With C, there's 7 choices. D only has 1, and B, the correct answer here, there are 8. The convention for depicting this sort of thing are to put the electrons in pairs. Okay, so it really kind of makes it easy to see with argon that there are 4 pairs there, especially compared to fluorine. That there's 3 pairs and then this 1 alone electron by itself. there needs to be another electron in that position there to complete that. The oxygen atom that's depicted here with the 6 electrons that are kind of equally spaced around doesn't really use that convention. And they did that on purpose to make it look, full. Really what you'd see would be 3 pairs, one at the top, one on the side, one at the bottom perhaps. And the second pair on the side wouldn't be there. It would be like the fluorine with 1 less electron. But that's what a chemically inert atom would look like. Oh. So early on, Nick said that he remembered ionic bonds, but he didn't know the other stuff, and he wanted to get more of that. So to start off with, the tutor here is asking him which of the choices here, sharing or transferring, represents ionic bonds. And so Nick responds correctly that ionic bonds is when there's a transfer. And when that happens, when an electron moves between, oh, well, it'll say that here. So just the idea that when these two elements come together, because of donating an electron from sodium to chlorine, they'll end up making an ionic bond, which is demonstrated here. And when that happens, when sodium's 1 electron in its 3rd shell is donated, its valence shell is now its second shell, which is full with 8 electrons. And the one that's given over to chlorine fills that spot that its valence shell needs. It has 3 shells, and its 3rd one out is valence one, which is now complete with 4 pairs of electrons there. Electrons are negatively charged, so when it's transferred over, it changes the charge of these 2 atoms. Sodium in this configuration is electrically balanced. It's neutral charge. Chlorine in this configuration is. When the electrons leaves sodium, it now has 1 more proton than electron, so it has a positive charge. And when that electron goes over to the chloride side, now there's 1 more electron than proton, and so that's got a negative charge. Those are ions, charged particles. Charged atoms are ions. If you're kind of paying attention to what I was doing, which was mangling things quite a bit, I used chlorine and chloride. When we're looking at this ion from the chlorine atom, when it's in its ionic form, we call it the chloride ion. So you'll hear me refer to chloride a lot. And I'm talking about the ion form there.
Do you consider ionic bonded molecules polar molecules, or are they? Is that only for?
They are beyond the polar.
Yeah.
We'll talk about polar in a little while.
Yeah. I know that like things like water is.
We'll talk about polar when we get to that part. So here's another question here. Okay, so we're actually not at 100% yet because Van Rung stepped out, but all of you have answered, so we'll go in from there. He comes back and you put his answer in. But again, looking at the distribution of answer choices here, nobody chose D, the none of the above, so you recognize that it had to be one of those. Which one of them is correct? C. Now, to some extent, this question seems to require you to know something about potassium. But really, we just looked at chlorine. So based on what we saw before, you should be able to see that chlorine, again, just has one spot. And so it's going to gain the electron that potassium loses.
Wait a minute, did I just miss a question?
Yeah, it's okay. So I got this case study from a website that I subscribe to that has case studies to be used in education. And so I downloaded the PowerPoint and I'm using it. I really should have adjusted this slide a little bit because I don't quite agree with what they have to say here. What they're saying here isn't incorrect, but I think they could have definitely stressed it a little bit differently. Sodium ions are in fact important in regulating blood volume and blood pressure. If you get too much sodium in your diet, then that means that your blood volume and therefore your blood pressure is going to be high. And the hormones that regulate those facts, volume and blood pressure, really tend to manipulate sodium across the or in the kidney, and that then leads to changes in blood volume and blood pressure. Okay. And then here it says that chloride ions can be used to balance the pH of the body and transmit nerve impulses. Those are the things that really have the problem. The pH of the body is regulated by an ion called bicarbonate more than anything else. Chloride is necessary for bicarbonate to get into the bloodstream. So yeah, it's involved in helping balance that, but it's not the thing that actually balances it. And then transmitting nerve impulses, really sodium is much more important for that than chloride. Chloride is part of one aspect of what happens in nervous tissue, but it is important in some aspects of higher functioning in the brain. And we'll talk about that when we get to that section there. But I need to change up this slide a little bit. So read this one slowly first. Okay, so one of the things I want to do is, in going through this, is to hit on some of the important things in biochemistry that we need to think about. And one of those is about protein shape. Now, I have these toys that I like to use that we can fold up and demonstrate protein shape. Okay. So what I've folded here is supposed to represent the shape of a protein. No protein actually looks like this, right? That's fine. part of what holds all this together we'll be talking about in a little bit. But there's this sort of curly-Q part here, what's called a helix, and there's this flat sheet here, what's called a sheet. And in what I have here, again, this is a made-up protein, but for it to fold like this, take on this particular three-dimensional shape, there would probably be an ion. It might be zinc or magnesium or something like that, but there might be some ion that plays a part in that. And it plays a part because of its charge. So there might be a magnesium ion right here. Magnesium is a positively charged ion, and it's attracted to some negative aspect in the helix shape of the protein, which folds it over like that. And that gives proteins a very specific shape. And so the second paragraph here is getting at the fact that there are a lot of diseases that have to do with misfolded proteins. So Alzheimer's disease, or Creutzfeldt-Jakob, which is basically human mad cow disease, and I have no familiarity with this insomnia thing, but apparently these are all conditions that depend on protein folding. Now, I don't know necessarily that Alzheimer's disease is caused by an ionic imbalance. I don't think anybody exactly knows. Creutzfeldt-Jakob disease is actually caused by ingesting a misfolded protein, usually from something else that has that disease. So when mad cow disease gets into the human population, it's usually because somebody's eaten brains of a diseased mad cow, which sounds like a really stupid thing to do, so why does anybody get mad cow disease? But it happens. So it's not directly about ions there, but ions are important in how proteins fold. So I know all of you can answer the question that Nick just interrupted Josh with, right? Because I know you've all rewritten a paragraph in that syllabus quiz assignment where you had to basically define what electronegativity is. What is it? Yeah.
The affinity of an atom to attract an opposite charge because of the valence shell that make up shell. So in the case of like water,
Well, you're going to get all the secrets, Mike. That's fine. We'll talk about water in a minute, but it's the affinity of a particular atom to the electrons that it's going to make a bond with. So in covalent bonding, atoms share electrons. In ionic bonding, electrons are completely transferred from one atom to another, but here they're shared. And electronegativity is a property of every atom, and how electronegative one atom is versus another will influence how they share those electrons, what their affinity is, how attractive an electron is to another one. Okay. Which is kind of defined right here. So, actually, I think the next slide is a picture here. Nope. Okay, this is a rather boring picture because it's two hydrogens. But one little difference in the way that our model is representing electrons and electron shells. Instead of a circle, an orbit, we're now seeing this gray area, which is representing an electron cloud, which is closer to what a chemist is really going to talk about when they're talking about atoms, but not really quite there. It just represents anywhere in this gray space we can find electrons. Okay, and the two red dots are just representing that there's a pair of electrons, one from either hydrogen, that are being shared. Since we're talking about this value electronegativity, which is a property of every element, every atom, two atoms of the same element are going to have the same electronegativity. So when those two bond together, they're going to equally share those electrons, okay, which is what we call a nonpolar covalent bond. So here's another question. I think we're just waiting on one more answer. Make sure you submitted your answer. Make sure your screen only has one letter on it anymore. If it still has four, then you haven't submitted yet. There we go. So we have some takers from all of them, but we have a little bit of more people chose A than any others. D came next, and then there's some takers from those in the middle. Which one's correct? Now, we just saw that when an atom makes a bond with itself, that's by definition a nonpolar covalent bond. There's two carbons making bonds with each other in this, so they're going to be that's going to be a nonpolar covalent bond. Also, there are certain bonds that are always nonpolar because the involved atoms have fairly similar electronegativities. And one, which is very important in what we're going to be learning in this course, is carbon and hydrogen. Carbon and hydrogen always make nonpolar bonds. Now, in this list, you can see, well, there's two oxygens in CO2, so wouldn't that also be nonpolar? The logic based on what we've covered so far in this case study, that makes sense. But in fact, in CO2, one oxygen is bound to the carbon and the other oxygen is bound to the carbon on the other side. So they're not bound to each other. They're both bound to the carbon. Now, a number of people chose sodium chloride. And from what we've already covered, I'm actually a little bit surprised that so many people chose that. When we were talking about ionic bonds in the definitions, in what was being spoken about, they mentioned salts. Right? Now, a salt is any compound or any ionic compound where the two components are usually a metal and a non-metal, and it's not going to have an H or an OH. So sodium hydroxide, NaOH, is essentially an ionic compound, but it's not a salt. Or HCl, hydrochloric acid, it's not exactly an ionic compound, but it's not a salt. Okay? Sodium and chloride, when they come together, usually it's something from the first two rows bonding with something with the last two rows. The last row is the noble gases, and they aren't going to bond with anything. So the second to last, I shouldn't say row, columns. So the column that starts with hydrogen and goes all the way through, or the column right next to that has magnesium or calcium are the two big ones we deal with there. If any of those bond with something in the column with fluorine and chlorine, those are usually going to be salts, ionic compounds. And then I explained away CO2. Magnesium oxide isn't exactly as ionic as this. It's not an ionic bond, but they're still pretty far apart. Here again, we have some atoms that are bonding with each other that are the same, and therefore their electronegativities are the same. Now, yeah, that's right. We'll get back to the presentation. One thing I didn't think about in terms of hold on a second. One thing I didn't think about in terms of the presentation here, the recording aspect. I want to switch from the presentation here to this screen here so I can put some stuff up. And what I want to start here is a list that is nonpolar bonds. Whoops. So when carbon binds to itself, oxygen bonds to itself, nitrogen bonds to itself, hydrogen bonds to itself, those are all going to be nonpolar. And then I just told you a second ago when carbon bonds to hydrogen. Now, if you have some familiarity with compounds, you might complain about the single line that are represented here. But all I'm talking about is when we have any bond between these. So if we have a carbon bound to a carbon within a larger molecule, or oxygen bound to an oxygen within a larger molecule. Or if we're talking about, say, like the oxygen molecule, what is in the air we breathe, that's still nonpolar in that there are two oxygen atoms bound to each other. The type of bond is a little bit more complex than what that suggests, but it still falls into the group represented here. We just saw hydrogen-hydrogen bonding in the picture that we were looking at a second ago, and then I just told you the carbon hydrogens are going to be nonpolar also. So I just want to start this list. We're going to talk about polar bonds next, and so I'll include that in another column here. This is when I would like to take a break, and as I've been doing this presentation with my other AP classes, after question 3 is a great place to stop. So we'll take a little bit of break, like I normally tend to do around the 3 o'clock hour for this class. Take about 20 minutes, be back in here at 10 after according to that clock, and we'll continue on with this stuff. So do whatever you want to with the next 20 minutes.